Hey everyone, welcome back to Calculus 3. This will be lecture 11 of the course, and in this lecture we're going to discuss arc length and curvature. So let's go ahead and jump into it. So this will be section 2.5, arc length and curvature. Now previously we saw, so back in Calculus 2, we discussed arc length. And we found there that for a plane curve with parametric equations, x equals x of t and y equals y of t, we found that the arc length of the curve when t is between a and b, so for a less than or equal to t less than or equal to b, the arc length, s, was equal to the integral from a to b of x prime of t squared plus y prime of t squared and the square root of that. Okay. So we found this, we went through this back in Calculus 2. Now, in vector form, if you think about what we've been doing with vector-valued functions, in vector form, if C is a curve in the plane, we'll say, and it's represented by the vector valued function r, t equal to x of t I plus y of t j. So if C is some curve in the plane represented by this vector valued function, then the formula for arc length is well, you could think of it as the same thing, but given what we've discussed recently, we could also write it as the integral from a to b of the norm of r. Okay, actually the norm of the derivative of r, right? Okay, so it looks like this. Okay, so this is just because that formula we discovered in Calculus 2 is it's basically the same idea as the norm of a vector valued function, right? So at the time we didn't know what a vector was, and so we couldn't put it in this notation, but now we see that in fact that's what we were talking about the whole time. Now, of course, in 3 dimensions, you can do the same thing. So, in space, if C is a curve represented by some 3-dimensional vector, and we'll just again write it out here just to be thorough. Maybe we've got x of t times the I vector plus y of t times the j vector plus z of t times the k vector, right? So in this case, we can we can identify the length of the curve between a and b as basically the same thing, but just with the k component thrown in as well. So it would be s equals the integral from a to b of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared, right? The square root of that whole thing with respect to dt. And this is, of course, the same thing as the norm of r prime of t, right? So the integral of the norm. Okay, and so let's do an example where we kind of use this information, but in the context of a vector-valued function instead of a function defined by a parametric equation. So let's let's do this one. Let's find the arc length of one turn of the helix given by, so this is going to be a helix, given by this function, r of t equals b cos t times the I vector plus b b sine t times the j vector plus, and then the last piece will be 1 minus b squared square root times t times the k vector. Okay, so this will this vector value function defines a helix. Again, we talked about what a helix was in a previous lecture, but so if you have your XYZ coordinate system here, a helix is, and it could be oriented in different ways, but typically it just is oriented up the z-axis like so, right? So it's just kind of a spiral shape, like a spring, that looks something like this. This is, of course, a terrible drawing, but you get the idea. So we'll start by differentiating r, right? So what is the derivative of r? Well, and all we have to do is just differentiate each of the components here, and it's relatively straightforward. So this will be negative b times the sine of t, I, plus b times the cosine of t, j. Now what about this thing? Well, this 1 minus b is just a constant, and then t is the variable. So the derivative here is just going to be the constant, right? The variable would be raised to the 0 power after we differentiate. So it'll be plus the square root of 1 minus b squared times k, right? So that's your derivative. Then we can integrate this to find the arc length, right? So 1 turn means 1 revolution. That's 2 pi degrees, right? So we will, and so obviously t is inside the trig function, so that 1 turn implies 2 pi. We'd be integrating from 0 to 2 pi. So s is equal to the integral from 0 to 2 pi of, now we know that it's this, it's the derivative, or sorry, the norm of the derivative of r, right? But so to do the actual calculation, we're going to have to plug it into, we're going to have to actually plug in the vector. So the integral from 0 to 2 pi of, right, so it'll be b squared sine squared t, right, so squaring each component, plus b squared cos squared t, plus, and then squaring that, we just get 1 minus b squared, and then the square root of all of that. And then with respect to t, naturally. Okay, and so this is a nice one because it cleans up a lot, right? So we can factor b squared out of this, and we get sine squared t plus cos squared t, and then plus 1 minus b squared, like so. Okay. And sine squared t plus cosine squared t is 1, so this is just the square root of b squared plus 1 minus b squared. So this is just the integral from 0 up to 2 pi of just 1, right? So it's just the integral dt. Okay, and so we can do that obviously easily, and that is just t, and the bounds are 0 up to 2 pi. So we can plug that in, and you would get 2 pi minus 0. So the arc length here, s, is going to be equal to 2 pi. All right, so the arc length of 1 revolution, or we'll say 1 turn of the helix, is 2 pi. Okay, so that's just an example, kind of a little bit of a review, actually. I mean, we sort of talked about this, as we said, in Calc 2, but then, I mean, we're just kind of putting it into slightly different notation here, or utilizing some different notation where it's now available. And also, I guess, extending the result into 3 dimensions, right? Because we hadn't really done that previously. Okay, so, all right, so moving on, we've seen already, right? We've already seen that curves can be represented by vector valued functions, right? And they can be represented by vector valued functions in different ways, right? Depending on kind of the choice of parameter. Now, time is frequently the most useful parameter. Right, we've seen, like in the example of velocity and acceleration, for example, those two, time was the obvious choice there, right? But just in general, when we're talking about motion along a curve, the parameter t for time, meaning time, is a fine choice, right? Sometimes, however, like for example, when we're studying different geometric properties of a curve, sometimes the convenient choice is not time, but is maybe something more like arc length, and that one being kind of denoted by an S. So sometimes arc length is the most useful choice of parameter. Okay. And so in those instances, we really need to, what we need to talk about is we need to talk about something called the arc length function, right? So how would arc length as a parameter work, right, when we're describing a function? That's what the next definition is all about. So in the case where we do want to have the parameter be something like arc length, how does it work? Well, let's define this. So we'll let C be a smooth curve given by r of t, some vector valued function, r of t, and defined on the interval AB. Okay. Okay. So we've got, just typical sort of intro statement. We've got C is a smooth curve, given by some vector valued function and defined on some closed interval AB. Now, for A less than or equal to T less than or equal to B, right, the arc length function is given by, okay, what's it given by? Well, it's given by the thing we just exactly discussed. So S of t is equal to the integral from a up to the parameter t, okay, t is between a and b, of the norm of the derivative of r. Okay, we saw what that is in 3D space, but let me just write it out again here. That's x prime of t squared plus y prime of t squared plus z prime of t squared, square root of that, integrated with respect to t. Oh, I'm sorry, this needs a change of variable. That should be a u instead of a t. My bad. Otherwise, that gets really confusing. So this is du. So r prime of u du, because the integral is going from a up to t, so you can't have t be inside. That would be a little awkward. Okay, and so this right here is called the arc length function. Right now, naturally, if your x, y, and z are real valued functions of t, then this integral, or sorry, in this case, real valued functions of u, then this integral is going to result in, and a is a real number and t is a variable, then this integral is going to result in a function. Okay, and that's why we say s is a function of t here. So the arc length s, right, the arc length s is called the arc length parameter. Okay, it's called the arc length parameter. Right, and now notice that here s will always be greater than 0. Okay, so notice that, right? This is obvious that this is going to be this is the norm, right? So this is going to be a positive valued function. Okay, so s will be greater than or equal to 0. Okay, so that's kind of the setup, right? So given a smooth curve with, you know, a vector valued function of t, right, kind of the vector value functions that we're used to, we can define an arc length function s of t by basically just doing this integral, right? This integral that we talked about back in Calc 2, and now we're kind of bringing back up. Okay, let's do an example. See how this works. Okay, so let's find the arc length function s of t for the line segment given by, let's write this vector valued function out, r of t equals, and then we'll call this, we'll do 3 minus 3t times I plus 4t times j. Okay, and for specifically 0 less than or equal to t less than or equal to 1. Okay, so we're going to find the arc length function s for the line segment here, r of t, it's defined by r here, on the interval 0 to 1. Okay, and secondarily, once we've done that, let's express r as a function of s. Okay, so then once we have the arc length function, let's go ahead and plug in the arc length parameter into r. So let's convert r to a function of s. Okay, so naturally we will, to find the arc length function, we have to do that. We have to run the integral on the norm of the derivative of r. So we have to find the derivative of r first, right? So r prime of t, that's just going to be the derivative of these two, right? And so it should just be negative 3 times I plus 4 times j. Okay. And so then what's the norm of this? Right? So what's the norm of that derivative? Well, in this case, there's no t's even included in the function, so it's going to be 3 squared plus 4 squared, square root of that, and so that's square root of 25, so it's 5, so it's a constant in this case. So in this case, the norm of the derivative of r is a constant. That won't always be true. It's true in this case, though. So s of t, then, is equal to the integral from 0 up to t of, let's write it all out, so it'd be r prime of t, right, with respect to, that's r prime of u, sorry, du. And so just plugging these things in, we get the integral from 0 up to t of, in this case it's the constant 5, like so. And so this is 5t, and then the bounds go from 0 up to t, 5u. I don't know how many times I'm going to make that mistake. Right, and so this is just going to be 5t minus 5 times 0, so 5t. Okay, so s of t is equal to 5 times t. Okay, so now how do we take this information and rewrite r using the arc length parameter? What we do is we say, okay, so s equals 5t, that implies that t equals s over 5. Okay, so r of s would be what? Well, r of t is 3 minus 3t, so r of s is going to be 3 minus 3, and then instead of t, we're going to put s over 5. And then you've got 4t, but instead of t, we're going to put s over 5. So 4 times s over 5. Like so. Right, and we could, of course, clean that up a bit better. Let's clean that up just a little nicer. So r of t, which was 3 minus 3t times I plus 4t times j can be rewritten as a function of s and it becomes this. It becomes r of s equals 3 minus 3/5 s. Dang it. It becomes this. 3 minus 3/5 s times I plus 4/5 s times j. Okay, and so this is only valid on the interval 0 less than or equal to s less than or equal to 5. Okay, s has to be between 0 and 5 in order for this to be an appropriate function. Okay. All right. Very good. Very good. So, one of the advantages of writing a vector-valued function in terms of the arc length parameter is that the norm of the function is then going to be equal to 1. Right? So one advantage of this is that the norm of r, the derivative of r, sorry, equals 1, right? Right, so that's advantageous, and we'll see why that's advantageous in a bit. But just to confirm this, let's take the norm of this derivative, right? So r prime of s is going to be equal to 3. Let's see, hold on one second. Yeah, so if we were to differentiate this, this would be negative 3/5 s times the I vector plus, it'd be just negative 3/5 I plus 4/5 times the j vector, right? So that's the derivative of r, and then the norm of r prime would be negative 3/5 squared plus 4/5 squared, right? And so then you would, of course, get 9 plus 16 over 25, which is just, 25 over 25, so that norm is 1. Okay, so just confirming that. Right, so for a smooth curve C represented by r of s, where s is this arc length parameter, the arc length between A and B is, okay, so let's kind of push through this. So for a smooth curve C, right, represented by r of s, right? So represented by r and parameterized by this this arc length parameter, right? The arc length between A and B, right? So specifically, that's what we use to derive this s. So that arc length is going to be equal to, okay, so the length of the arc is equal to, now we can just kind of write out what this is. This is going to be r prime of s ds, right? And of course, we just showed that this is 1, right? So the integral from a to b of just ds here. And of course, when we do that, we know we're going to get b minus a, right, which is equal to the length of the interval. Right on the next line. It's just the length of the interval. Okay, so for a smooth curve C, represented by this r of s, where s is the arc length parameter, of course, the arc length between a and b is equal to the length of the interval ab. Okay, which is extremely convenient. Extremely convenient. Okay, we'll see some examples of that and of why that's so convenient in a second. But that's nice. All right. This should remind you of radian measure from trigonometry, for example. All right. Why did we like radian measure? Well, it aligns with the angles. All right. So, all right. So, theorem. Okay. Theorem. If C is a smooth curve, given by, now I'm going to write just the 2D version. Okay, or, so that's the 2D version or 3D version. Right, it'd be the same. The theorem remains the same. So if C is a smooth curve given by this vector valued function parameterized by arc length, and I'll say that specifically where S is the arc length parameter, then the norm of the derivative of R is equal to 1, and moreover, if t, right, if t is any parameter, for the vector valued function r, okay, if it's any parameter for the vector valued function r such that the norm of t equals 1, then t must be the arc length parameter. And what is this saying? Well, it just says that basically the arc length parameter is unique. Right? There's only one such parameterization of R where the norm is equal to 1. Okay. Okay. So there's no other way to parameterize R that's distinct from this arc length parameter while maintaining this condition that the norm is equal to 1. Okay. Excellent. Now, where does this kind of come into? I mean, we talked already about, how t is generally speaking, time is generally speaking the best parameterization, for, looking at motion along a curve, for example. When is arc length a good parameterization? Right. Well, we kind of said, arc length is a good parameterization whenever we're studying like geometric properties of a curve. Okay. And so one such application is using arc length parameter to find the curvature of a curve. Okay. So an important application of arc length parameter is in finding the curvature. Okay. And what is the curvature? Well, in sort of like lay terms, it's the measure of how sharply a curve bends. Okay, so this is one of the most important applications of this arc length parameterization. Right, so what do we mean by curvature? Well, the measure of how sharply a curve bends is like one way to say it. We'll get into something a little more rigorous in a second, but just intuitively, if I have some curve in space like this, let's say I've got a point P here, and I got another point up here, Q. All right, the curvature at P is greater than it is at Q. Right, and specifically because the curve bends more sharply at P. Okay, it bends more sharply, but you can kind of see that this is a sharper curve than the more and then Q is a more gentle curve. Okay, so this idea of curvature. Okay, so let's define curvature, and we'll see, of course, where arc length parameter comes into play here. Okay, so what do we mean by curvature? Okay, let's let C be a smooth curve. Okay, in the plane or space. Okay, given by R of S, where S is the arc length parameter. Okay, so we've got this smooth curve C in space described by R of S, where S is that arc length parameter that we just discussed. Then the curvature at S, that's an AT, at S is given by, how do we calculate it? Well, it's denoted with a K, okay, and it's equal to the norm of dt ds. Okay, now what is this t? Well, remember this is the unit tangent vector. Okay, so it's going to be, the curvature is going to be the norm of the derivative of the unit tangent vector. So another way to write it might be like this, t prime of s. Now, the unit tangent vector has to be parameterized by the arc length parameter. It has to include the arc length parameter in order for this to work. Okay, and so let's write this also where t is the unit tangent vector. Okay, right, and so that's a fairly simple definition. I mean, so if we want to know the curvature at the point S, then we have to find the unit tangent vector, evaluate it at S, and differentiate it, and then take the norm. Okay, so let's do maybe we'll do an example of this. Okay, so in this example, let's pull up something that's familiar to talk about this. So we're going to talk about just a circle. Right? So what we're going to do in this example is we're going to show that the curvature of a circle of radius r, okay, is k equals 1 over r. Okay, so in the case of the circle, we see that the curvature is constant, right? Remember what a circle is. Right, so we all kind of know what a circle is, but sometimes it's useful to try to draw a decent one here so we can reference it. Okay, so not too bad. Okay, so so no matter where you're at on the circle, the curvature, notice, is exactly the same. Right, the steepness of the bend in this curve called a circle is constant. It never changes. Right, if it did, so here you can see constant curvature. right? If the curvature did bend, right, then we would have something maybe that looked more like this, for example. Right here you've got a curvature that is larger, a larger curvature here than you have up at the top, for example. Right, but this clearly isn't a circle. It's more like an oblong shape. Okay, and so if the curvature is not constant, you end up with shapes like, that appear circular, but not precisely a circle, right? So this obviously kind of resembles a circle, but it isn't a precise circle. So in the case of an actual circle, the curvature is a constant. And moreover, you can see that the curvature is the inverse of the radius. So the larger the circle, the smaller the curvature. And if for very tiny circles, so for very small circles, the curvature is quite extreme, if you look at that. Right? Whereas for larger circles, the curvature, if you compare the curvature here versus the curvature of this little point here, very different, obviously. Okay, so what we want to show is that the curvature of a circle of radius r is 1 over r. Okay, and so for this, we're going to basically just apply the previous definition of curvature. Okay, we'll have to kind of go through the arc length parameterization and everything, so we'll kind of wrap everything into this example. Okay, and so we're going to start by just assuming that our circle is centered at 0, 0, right? So we'll use something like this. Okay, so centered at 0, 0. Actually, I'm just going to draw another circle here because I don't want that other stuff. Let's just draw one more circle. Okay, so let's see if I can do another one. Yeah, that's not too bad. Okay, all right, so I've got my circle, and it's centered at 0, 0. And we're going to let xy be any point on the circle. Okay, so I'm just going to draw in a convenient spot just for the drawing's sake. Okay, xy is going to be any point on the circle. Okay, and then we're going to let s denote the arc length basically from r0 up to xy. So s is the arc length from, and this would be the point r, 0, up to xy, whatever xy happens to be. Okay? And then, of course, implicit in this is some kind of array here and an angle that's swept out. And we'll call that angle theta, right? So let theta be the central angle of the circle. Okay. Okay, and so using this kind of a setup, right? Using this kind of a setup, we can come up with a vector equation for this, right? We could write specifically, this would be r theta is equal to r cos theta times the I vector plus r sine of theta times the j vector. Now notice, as theta varies, you get every point on the circle, right? And that's basically what that means, right? That when we say that the circle can be represented by this vector value function, that's what that means. Okay. All right, so good. Now what we need to do is, so this, notice this is, this vector valued function is parameterized by theta, right? We need it to be parameterized by the arc length, s. So we need to calculate the arc length parameter. Okay, so we need to calculate the arc length parameter. Now, probably better to say the the arc length function, right? But yeah, we'll write it like that. Okay, so we need to calculate the arc length function. So S of theta, okay, is equal to the integral from 0 up to whatever theta happens to be of the norm of the derivative of theta d theta. Okay, this should be a u. Dang it. Sorry, I did that again. I knew I would do it again. So s of theta is equal to the integral from 0 up to theta of the norm of r of u du. Okay, and so we can plug all of these pieces in now. So 0 up to theta, and now we need the norm of the derivative here technically, so we have to differentiate this, and so let's write that out in here. So this would be negative r sine of theta, right, I plus r cos theta j, and we need the norm of that. And these are all u's. Scrapers. Sometimes you get something in your head and you just can't shake it. Okay. So what's that norm? Let's calculate that norm. So this is 0 up to theta, and now this will be r squared sine squared u plus r squared cosine squared u, and then the square root of that du. Okay, and so just kind of like previously what we saw, this is, you can factor out the r squared, right? And so you have 0 up to theta, and then this is r squared, and then it's sine squared u plus cos squared u du. And so this just becomes the integral from 0 up to theta of, well, it's a square root of r squared, so it's just r. Okay, so let's flip the page here. Okay, and so what do we have? Well, so what we have here is 0 up to theta of r du. And so, of course, this is r times u, where u goes from 0 up to theta. And so you get r times theta minus r times 0, so just r theta, right? Okay, and so what do we have here? So s is equal to r times theta, and well, that implies that theta is equal to s over r, right? And so this is how we can parameterize here. Okay, and so we'll input this into our original function, right? So we had r of theta equals r cos theta times I plus r sine theta times j, right? And so what we can do is we can reparameterize this using the arc length, and so what we would have instead is that r as a function of s would be equal to r cos theta, and now instead of theta we're going to put in s over r times I plus r sine of theta, or r sine of s over r times j. Okay, so now we've got r written as a function of s. Now remember, this is a little confusing because the function is named r, but this little r in here is just the radius, right? So don't be confused by that. Okay, and so now we have the function, the vector valued function, parameterized as in s, and so we can differentiate it, and we can use that result to find the curvature. Okay, so then what do we need to do? Well, we just need to differentiate this thing. R prime of s, right, is equal to what? Well, it's just gonna, remember this is just a constant, right? So so we'll have to use the chain rule here. S is a variable, r is a constant, and so we'll do the chain rule, and what'll end up happening is that this r will end up canceling with what's out here. And so what we'll get here is negative sine, I don't know why I wrote a theta there too, negative sine s over r times I. And then the same thing will happen over here when we differentiate this. This will become a cosine s over r times j. Okay, so again, that's just the chain rule. So you differentiate the outside function, which is the sine function, and then you differentiate the inside function with respect to s, which is s over r. Okay, and you just get 1 over r. And then the r's cancel. That's what's happening there. Okay, and it should be kind of obvious, but notice here that the norm here, as we said it would be, is equal to 1, right? In this case, it is, so it'd be negative sine of s over r squared plus cos s over r squared, right? And so that's just sine squared plus cos squared equals 1. Okay, so we've got that piece. So just kind of double checking that. So now what we want to do is we need to find that unit tangent vector. Now, do we remember how to find the unit tangent vector? Well, the unit tangent vector, recall, right, was equal to r, the derivative of r, divided by its norm. Right, this is from the previous section. We talked about the unit tangent vector, defined it, and then kind of talked about what it was all about, how it moves in the direction of the curve, always that kind of thing. And so you should be able to visualize what the unit tangent vector looks like in our setup here. The unit tangent vector is going to be a unit vector moving in the direction of the curve for any value of s. Okay, so when the arc length is that, then the unit tangent vector will look like that. Okay, and so to find that unit tangent vector, or an expression for it, we need to use this sort of formulation. We need to take the derivative of r and then divide that by the norm of that derivative. Okay, and so this is relatively easy to do because the norm is 1. So basically it's just the derivative, isn't it? Right, so this is just negative sine of s over r times I plus cosine of s over r times j. Okay, so that's the unit tangent vector. Very nice, easy to find, specifically because this norm is already 1. The norm of this derivative is 1. And that's a lot of the reason why using the arc length parameter is convenient. Then the curvature is just the norm of the derivative of this. So k is just equal to the norm of the derivative of the unit tangent vector. Okay, and so what is that? Well, it's just this guy here. Well, first we got to different. Well, let's see. Well, yeah, we can do this in one step, I think. So we have to calculate the derivative of this inside the norm brackets here, but that's really easy to do. It's just negative 1 over r cosine of s over r times I. And then over here it becomes negative also, doesn't it? Minus 1 over r times the sine of s over r times j. Okay, so that's really just differentiating here. And so usually we might find the derivative of t first and then kind of plug it into the norm expression, but that's okay. In this case, this all works. We know what we're up to here. And so then we can take the norm here, and that's just going to be the sum of squares of the components, take the square root of the sum. So it'll be, I'll just write it all out first, negative 1 over r cos s over r squared plus negative 1 over r sine of s over r squared, and then we're going to take the square root of that. Okay. And very nicely we can rewrite this, right? So this would be 1 over r squared, right? And I can factor that out of both of those. And then what I get is cos squared s over r plus sine squared s over r. And of course that's equal to the square root of 1 over r squared, which gets us 1 over r. Okay, so the curvature here is 1 over r, which is what we set out to show, right? That's what we kind of set out to demonstrate. So so we'll write this in. So the curvature of a circle is constant and equal to k equals 1 over r, where r is the radius. Okay, so that's kind of a proof of that. Okay. All right. Excellent. Okay, so let's good. Let's move forward. So I think we've kind of got the idea of how to calculate the curvature. Seen examples of that now. So in this previous example, we found the curvature by applying the definition directly, right? So we found the unit tangent vector, we differentiated it, we took the norm. Okay. That's not always the most efficient way to go about finding the curvature. So sometimes, it's convenient to bypass this arc length parameter. And in that case, we can use a parameterization, just an arbitrary parameter t, right? It doesn't have to be arc length parameter, right? So if we need to find the curvature and it's not convenient to identify the arc length parameter, then we can do this. All right, so here's the theorem. Okay, so if C is a smooth curve, given by r of t. Okay, now remember t is just some arbitrary parameter. Then the curvature of C at t is given by, okay, so the curvature can also be calculated in terms of an arbitrary parameter as the norm of the derivative of t, the unit tangent vector, divided by the norm of r, the derivative of r. Okay, so you can do it this way. So you find the unit tangent vector, differentiate it, take the norm, and you divide that by the norm of the original function r, derivative. Another way to do it, another way equivalent expression would be to take r prime of t crossed with the second derivative of r. Okay, and then take the norm of that. Okay, and then divide that by r prime of t cubed. So, yeah, I mean, that's kind of why the arc length parameter is so nice, because it's literally just the derivative of the unit tangent vector, the norm of that thing, right? So basically take all this out, right? If t is the arc length parameter, then it's that. Otherwise, you got to deal with all this, which may or may not be a challenge, depends entirely on the function you're looking at. So let's do an example and see kind of where this can be challenging. Let's take an example here. Let's find the curvature of the curve given by, and then we'll use this guy here, r of t equals 2ti plus t squared j minus 1/3 t cubed k. Okay, so there's our function, our vector valued function r, and here it's parameterized by just t. And so what we would say here is that it's not clear whether the parameter t represents arc length, so we will proceed by calculating this the hard way, right? So we can't just calculate the unit tangent vector. So what we're going to use is we will use the unit tangent vector derivative, take the norm of that, and then divide that by the derivative of the vector r's derivative the derivative of vector r, and that's going to be our k, right? So this is the formulation we just talked about, right? So we're going to use this. Okay, so let's go ahead and do this. We're going to need the derivative of r to start with, because that's going to be required to find t. So r prime of t, right? That's going to be the derivative that we're interested in. We got to differentiate this. And so we get 2i plus 2tj. And then what happens here? Well, this would be minus a third divided by 3 t squared. So this is just going to be minus t squared k. All right, so that's our r prime. The norm of that is what? And here's where we'll start to introduce some complexity into the expressions. All right, but this is going to be basically 4 plus 4t squared plus t to the 4th. Okay, and then this one actually, if you look at this closely, you'll note that this is t squared plus 2 quantity squared. And that helps a lot, right? Because then you can ditch the radical, and this is just t squared plus 2. Okay. All right, so that is r prime and the norm of r prime. Okay, things that we'll need. So this will eventually be the denominator of the curvature expression. But now we need to find t and then differentiate it and then calculate the norm. So what is t? Right, t is, well, it's r prime of t, okay, divided by its norm. Okay, so it's basically take the norm of the derivative of r. Okay, and so we can just write this out. We have all of the pieces here. We've got 2i plus 2tj minus t squared k. That's the numerator, and then this thing down here, t squared plus 2. Okay. All right, so that's you can think of that as the derivative, or sorry, that is our unit tangent vector. Now we need to calculate the derivative of this. Okay, so you can see this is going to get a little bit hairy because, in fact, I'm going to switch to another sheet of paper. This is going to get hairy because this expression is a little messy, right? So if t is 2i plus 2tj minus t squared k, and that's all divided by t squared plus 2, right? You got a unit, sorry, you have a vector as the numerator, and then you've got you have a vector value function as the numerator, and you've got a real value function as the denominator. And so what we can do here is we can actually use the quotient rule from calculus 2, okay, to calculate this derivative. So what we'll do is we'll do kind of the low d high minus high d low divided by low squared. Right, so it'll be low, that's the t squared plus 2, times the derivative of the top function. Okay, so you got to remember you got a vector here, minus high d low, right? So it'll be 2i plus 2tj minus t squared k. Again, this is a vector, times the derivative of the bottom. And then the whole thing is divided by the denominator squared. Like so. Okay, so that's kind of the setup. Now, fortunately, these are very simple derivatives. It's just the expression is a little bit more convoluted than what we might like, but they're relatively straightforward derivatives. Right, so the derivative of this function here is just going to be what? It'll be 2j minus 2tk. Right, so the components differentiate really easily there. And then here we'll have 2i plus 2tj minus 2t squared k. And then the derivative here will just be 2t, won't it? Yep. And then you've got t squared plus 2, quantity squared on the bottom still. Okay, and so now we actually have the derivative now, but we need to simplify this thing. And so what can we do? Well, we can just start to like kind of multiply this all out. Okay, so let's see. I think first thing we'll do is just kind of multiply this out. Well, we'll multiply these two pieces out and those two pieces out. Okay, so I get 2t squared plus 4, and that's times the j vector here. And then I get plus, and this will be negative 2t cubed, so this times that, and then minus 4t, that's times the k vector. Okay, and then kind of moving over to the other piece here, I'm going to put, I'm just going to write minus here, and then it'll be 4t I plus 4t squared j, and then minus 2t cubed k. Okay, and then all of that naturally over the t squared plus 2 quantity squared. Okay, and now I can just sort of simplify everything down here. Okay, and so basically I need to combine all of the I components, the j components, and the k components. All right, and so when I do that, I get negative 4ti, that's right here, there's no other i's here, so, and then the j components, I would get plus, and I'm just going to bracket it just so that we can keep track of it, 2t squared plus 4 minus 4t squared. That's the j's. Okay, so you've got these two here and then that one. And then it's going to be plus, and then it'll be negative 2t cubed, so this guy here, okay, minus 4t, and plus 2t cubed. And that's all k. Okay, so very good. So we've got everything kind of organized now, and then of course t squared plus 2 quantity squared on the bottom. All right, so now can we simplify this down? Of course, a lot of that stuff's going to drop out. And so we get negative 4ti plus, and then this thing here can simplify down to 4 minus 2t squared j. And then this one, these two cancel out, and you're just left with minus 4tk all over t squared plus 2 quantity squared. Okay. All right. So this is the derivative. Now remember what this is. This is t prime. This is the derivative of the unit tangent vector. Now what's the norm of this thing? Now, the norm okay, the norm is, we got to square everything. Basically, add it all up and square everything. So it'll be 16t squared plus, and I'm going to square this all out here. So this will be 4t to the 4th minus 16t squared, and then plus 16, right? So if you just kind of square that out. And then this other one is plus 16t squared. And then, of course, the bottom becomes t squared plus 2 squared, quantity squared, squared. Yeah, so you get that. All right. Now all of this cancels and simplifies dramatically, right? So this would be, up top here you got 16t minus 16t, right? So those two are gone, and then you're stuck with the 4t to the 4th, and then you've got the 16t squared, and you got a plus 16 up top. Okay, and then I can take the bottom, and that's still inside the radical, and I can take the bottom out of the radical and lose one of the squares here. So this would be t squared plus 2 quantity squared. And let's see, we can factor a 4 out of here. Let's do that. So I get t to the fourth plus 4t squared plus 4. And that's t squared plus 2, quantity squared. That's still the square root. And so let's see. Switch pages again. So here's what I have. I've got 4, and then t to the fourth plus 4t squared plus 4, square root, and then all over t squared plus 2, quantity squared. And so what can I do with this? Well, this is a sum of, this is well, this is 4 times, what is it, t squared plus 2 squared? Yes. Convenient. Yep, that's right. And so what I can do here is I can remove the radical now and rewrite this as 2 times t squared plus 2, and then that's all over t squared plus 2 quantity squared. And of course I get the cancellation, and this will just be 2 over t squared plus 2. Okay, so this is the norm of the derivative of t. Okay. All right. So we have all the ingredients now to calculate the curvature. So you see this is a much more involved process when the parameter is not the arc length parameter, right? Specifically because these norms, they tend to like kind of blow up into algebraic nightmare messes, right? And so that's kind of what's happened here, right? But I mean, you can do it still. I mean, the derivatives are relatively simple. It just becomes algebraically messy. So then we would say that the curvature K is, let's see, so it's K equals, and it's remember what this is, so it's the unit tangent vector parameterized with t, the norm of the derivative of that, divided by the norm of the derivative of r. Okay, we have these pieces now. So specifically the numerator is 2 over t squared plus 2. And the denominator we found previously was just t squared plus 2. And so what we have then is that k is equal to basically 2 over t squared plus 2 squared. Okay, so we can see here that k is a function of t, right? In this case, k is a function of t, and hence the curvature is not constant. So k is a function of t, and therefore the curvature is not constant, right? Right, remember when we looked at the circle, we saw constant curvature, and specifically k was equal to 1 over r being some constant value, the radius of the circle. Right, but in this case, k is not a constant. It depends on where you're at on the curve, naturally. Right, and so you can see that in the expression of k as 2 over t squared plus 2 quantity squared. That t in particular, for different values of t, the curvature would be larger or smaller. All right. Okay, very good. I think that's going to do it for this section. And so next time, in the next section, we'll get into, we're going to switch gears and move into functions of several variables. So we'll kind of leave behind vector-valued functions for now and move into the calculus of multivariate functions. Okay, so kind of a different way to describe objects in space or functions in space. So, okay, I think we'll leave it there, and we'll see you all next time. Take care.